So we're going to start off old school. This problem you should be able to do in your sleep. You got 50 milliliters of a 0.2 molar solution of benzoic acid. K is 6.3 times 10 to the negative fifth, find the pH. This you should be able to do in your sleep. What's the reaction going to be?
Benzoic acid.
You can just write it as HA. You don't have to know the formula. HA. What's it going to turn into?
H plus
H plus anions. Literally, that's all you have to do for the reaction part. Okay? You don't need to write out the full thing. Just do this. If you want to throw in the water and mix that hydronium ions, that's cool too. Okay? Doesn't matter. Whatever you want to do. There's your reaction. Notice this is going to be important. We're not titrating this. We're not adding hydroxides. Nothing. This is just all we have is a beaker of benzoic acid. That's it. So, just like you've done before, old school. This is 0.2 molar, 0, 0, minus x, x, and x. You get 0.2, x, x. Old school. Hey, literally, this should go, Mercap, I got this. You should feel utmost confidence in this process at this point. Should be absolutely spot on. So, x, so your Ka is going to equal x squared over 0.2. And this is going to be important. When you get x, you're finding two things. What is x giving you? The concentration of hydronium ions and the anion. Okay, you're getting two things. So to save you some time, if you do all this, you're going to get x, and then you're going to take the negative log of that. And trust me on this one, you're going to end up with a pH of 2.45. Okay? Now, why can't I just take the negative log of 0.2 to get my hydronium ions? Or my pH? All right? Strong. This is not a strong acid. It's weak acid. Only some of it's going to ionize. Okay? Cool. Got this. Now we're going to make it complicated. But not bad. So now I want to calculate the pH after okay. Now we're going to do titration. So this is why I had you all have this visual of what's happening in labs before we got into this theoretical part. So visualize this. Here's this beaker. You had the 50 milliliters of the benzoic acid. And this is important. Is this existing as separate ions or the molecular form of the acid? Molecular form. It's a weak acid. Okay? Out of 100 molecules, 3 of them might exist as separate ions. Okay? 97 of them are existing as the molecular form. I basically don't have any anions to speak of. Okay? But now, to this, I'm going to add some hydroxide ions. Am I going to worry about the sodium?
No.
Can care less. Sodium is not part of the story. Nothing personal. I don't care. It's not part of the story. Now we're going to do the reaction. So here's what's different in terms of the reaction. I'm going to still, and now notice I'm going to write this as the molecular form of the acid. I'm not going to write it separate because it's the molecular form. I'm going to react the hydroxide. I don't care about the sodium. Don't care. Not part of the story. Is it there? Yes. Don't care. Now, what am I going to get out of this?
Water. H2O.
Water and the anions. So, as I add the base, this is important. What's going to happen to the amount of molecular acid in the solution?
Decrease.
It's going to decrease. What's going to happen to the amount of anions in the solution? It's going to increase, right? One concentration is going to go up, the other concentration is going to go down. Okay? Right? Now, because this is a stoichiometric relationship, you are absolutely forbidden from working in molarity. Forbidden. Bad. You could work in millimoles, you could work in moles. Those are the only two options that you have. Personally, I work in millimoles because I don't want to go through the hassle of dividing by 1,000. So, let me show you how this is going to play out. So, initially I had 50 milliliters of my 0.2 molar solution of my benzoic acid. I take 50 times 0.2, I get 10 millimoles. Okay? That's the millimoles of acid that I have. On the hydroxide side, I have 15 milliliters of a 0.2 molar solution. I'm going to take 15 times 0.2, I'm going to get 3 millimoles. My anion concentration starts at 0. Right? Now, if you're going, oh, Burkham, this sucks. Can't do it. I cannot do the millimoles. Fine, work in moles. The only thing that changes is you're going to be dealing with a whole bunch of zeros and decimal places. Okay? Which actually, you're probably going to make more mistakes because you're going to lose track of decimal places and zeros and things like that. Now, here's the point of the story. How much of the hydroxide is going to get used up? All of it. That's what's going to run out first. So I'm going to go minus 3. How much of my acid is that going to consume? 3 of it. How much of my anion am I going to add? 3. So this is going to become 7, 0, 3. Millimoles, millimoles. Now, this is the next decision that you have to make. I had 15 milliliters of my acid, and I had 15 and 50. So my total volume is 65 milliliters. Okay? That's the total volume, because I had 50 and I just added 15. This is what you need to decide. You can go Ka equals the hydronium ion concentration times the anion concentration divided by HA. Okay? I need the hydronium ion concentration. So my anion concentration is going to be 3 millimoles, divided by 65 milliliters. And the concentration of my acid is going to be 7 millimoles, divided by 65 milliliters. Because I need concentrations. Now, conveniently, what's going to happen to the 65 milliliters?
Dead. Cancel.
Those cancel out. So basically, what are you left with? 3 over 7. Okay? So you know what the Ka value is. That Ka value is 6.3 times 10 to the negative 5th. So 6.3 times 10 to the negative 5th is going to equal the hydronium ion concentration, which you don't know, basically times 3 divided by 7. So you can take 6.3 times 10 to the negative 5th times 7, divide that by 3, get your hydronium ion concentration, and then take the negative log of that. Okay? So you multiply by 7, divide by 3, and then take the negative log of all of that. So if you're a Ka purist, this is your wheelhouse. But there's another option. And this is what's known as the Henderson-Hasselbalch equation. And this is on your equation sheet. So your pH equals the pKa plus the log of your anion concentration divided by the concentration of your acid. Okay? This is actually faster and simpler because you don't have to do a whole bunch of algebra. But some people go, like, this is like cheating. Okay, if you want to call it that way, fine, don't be judging. Now, the beauty of this is that you only have to do this one time. So somebody take the negative log of 6.3 times 10 to the negative 5th. Exactly?
Yep.
Okay, so this is going to be 4.20. That's my anchor. That number is not going to change. That's 4.20. Then all I have to do in this case is take the log. Now, technically, that's my anion concentration divided by HA. Technically, that's 3 over 65, and that's technically 7 over 65. But again, what's going to happen to my 65s?
Bye-bye.
65s cancel out, basically you're taking the log of 3 sevenths. Now, bigger idea. When I take the log of 3 over 7, am I taking the log of a number bigger than 1 or less than 1?
Bigger. Less. Find out
Less than 1. 3 over 7 is going to be log of a number less than 1. Log of a number less than 1, is that a positive or negative number?
Negative.
It's a negative number. So my pH is going to be less than 4.2 because I'm taking the log of a number less than 1. So if you do all this, you get 3.83 as your pH. Okay? Next one's easy. Okay? Next one's easy. On the next one, it's like I'm starting all over. I'm going to add 25 milliliters of a 0.2 molar solution of sodium hydroxide. Now that we know the process, this is going to go a lot faster. Oh, right, Burkamp, we got this. Rice chart, cool. Reaction, HA plus my hydroxide is going to yield water plus my anion. I'm going to work in millimoles because it's faster. Okay? So I know I have, if you go back up, I know I have 10 millimoles of my acid. That hasn't changed. So I have 10 millimoles of my acid. I take 0.2 times 25, I get 5 millimoles.
You get 5 millimoles.
I do. And 0. Oh, cool. Minus 5 millimoles, minus 5 millimoles, plus 5 millimoles. This becomes 5 millimoles. This becomes 0. This becomes 5 millimoles. How much have we neutralized?
5 millimoles.
Half of it. Oh!
Ooh, special rule, special
Oh, special rule, special rule. Okay? When you're half neutralized, your pH equals your pKa,
Cinema.
plus the log of your anion concentration divided by the concentration of your acid.
The Henderson law.
Oh, that's 5 millimoles, technically over 100 or over 75 milliliters. That's 5 millimoles, technically over 75. Well, why do I not even need the total volume?
They delete.
They cancel out. I'm taking the log of 5 over 5. What's the log of 5 over 5?
0.
Log of 1, which is
0.
So guess what? My pH equals my Ka. Half neutralized. Cool. Now, I got to hammer through this fast. Now, I'm going to add 50 milliliters of sodium hydroxide. Same reaction, water plus the anion. I got 10 millimoles of this, and this is still that 0.2 molar solution. This is 10 millimoles, that's 0. Here's my reaction. How much of my hydroxide is going to get used up?
All of it.
All of it.
All of it. How much of my acid is going to get used up?
All of it.
0, 0. Now, I've got to go through this real fast. I'll work through this all tomorrow. Is this anion going to react with that water? Yes, it absolutely will.
Yes, it
Why?
Strong
It's the conjugate base off of a
Weak acid.
weak acid. So here's what you do. You start a secondary reaction. The anion reacts with the water, and what are you going to create?
The weak acid.
The acid and
OH. Wait, we just did this.
hydroxide. Oh, we just did this.
Bert, this is an endless loop.
No.
This is groundhog.
Here's your reaction. Now, here's the story, and I know I got to hammer through this fast. You need the concentration of your anions at this point. You have 10 millimoles. Now you have to go back to being concentration. So you need to take the 10 millimoles and divide that by the total volume. And the total volume was 100 milliliters at this point. So this becomes 0.1 mole. So you take the millimoles divided by the total volume. Now, you've done this before. On the assignment that I just gave back, you've done this calculation. You know what to do. How much of this is going to get used up?
All of it.
Nope, none of it.
None of it.
Some of it, X and X.
Oh, terrible shot.
Now, but here's the story. What's the anion acting as? Conjugate base. You need the Kb value, but you don't have the Kb value.
We have the Ka value.
But you have the Ka value.
And we know
Neutralization of water.
14.
Oh! So, I'm going to do Kb equaling x squared over 0.1. The Kb value is going to be 1 times 10 to the negative 14th
Divided by the Ka.
divided by the Ka values. Now, when you get x, what are you finding?
Hydration.
Hydrogen
Hydration.
ion concentration. Okay. Now, if you if you look at this and go, I have no idea, I would spend a lot of time tomorrow going over this.
Oh, I have no idea.
So it's like